In Module 3, we look at elasticity. I'm sure you're familiar with this concept from microeconomics. Here we'll look at it from a mathematical perspective. Unlike the previous module, this module will be quite short. Economists are often interested in how one variable changes with respect to another. If we consider the changes in terms of percentage changes, then we're dealing with elasticities. For example, if we look at the percentage change in the quantity demanded with respect to the percentage change in the good's own price, we have price elasticity of demand. If the price change is for another good, a complement or a substitute, then we would be considering the cross-price elasticity of demand. And on the supply side, if we consider the percentage change in the quantity supplied with respect to the commodity's change in price, then it's the elasticity of supply. Let's see where derivatives fit into this picture. We start with a basic formula for elasticity. Let's look at it in terms of the elasticity of demand. We have the percentage change in quantity demanded in the numerator and the percentage change in the price in the denominator. We can expand that. Of course, the numerator and denominator are both times 100, but they cancel out. In the numerator, we have the change in quantity demanded divided by the quantity demanded, and in the denominator, the change in price divided by the price. We can rearrange that. So the price here goes into the numerator, and the quantity demanded here goes down into the denominator. We can expand the numerator. The change in the quantity demanded is the new quantity demanded, P plus delta P, minus the original quantity demanded. We use this formula when the change in price is small but finite. So that's the average elasticity of demand. We'll apply that formula in the second part of example 12. However, the form we're interested in here is where delta P tends to 0, and we have what's known as the point elasticity. Going back to this formula up here, you'll recall from lecture 4, this is just another form of the Newton quotient. So when delta P approaches 0, that second term will be the first derivative of the demand function. So that second term will be the first derivative of the demand function. That gives us the point elasticity of demand. We have P on the quantity demanded times the first derivative of the demand function. If we can consider this in general terms, we have the following formula. Variable x that changes and the function f of x that changes as a result. In the previous cases, x was the price and f of x was the demand function, but this is more general. The formula represents the elasticity of f of x with respect to x. In example 12, we apply that to the price elasticity of demand. It's quite a simple calculation, and you can go to that video at the end of this module. Elasticities can be positive or negative. For example, the price elasticity of demand is negative. However, the cross-price elasticity for a substitute is positive, as is the elasticity of supply. Consequently, it's useful to think of the absolute value of elasticity if we want to define its characteristics. The absolute value of elasticity takes values from 0 to infinity. Let's look at that on a number line. When the absolute value of elasticity is greater than 1, the function is elastic. So that's this range here. In the case of elasticity of demand, the absolute value of elasticity is greater than 1 when there are lots of substitutes. If the price goes up, then there's a big response. People go elsewhere. If the absolute value of the elasticity is less than 1, the function is inelastic with respect to x, this range here from 0 to 1. In the case of demand, inelastic goods are those where a change in price has little effect. These can be essential goods. For example, price of petrol goes up in the short term, demand is inelastic. Or they could be goods that people have some dependence on, for example, cigarettes. The tax on cigarettes has to be very high in order to affect demand. The values of 0 and infinity are the values of 0 and infinity for elasticities are idealized cases. If the elasticity is 0, a change in x doesn't affect the function at all. If a function is perfectly elastic, the smallest change in x causes an infinite change in the function. For example, in a perfectly competitive market, if the producer increases the price by a small amount, demand falls off to zero. In the case of economics and demand, an interesting relationship is the relationship between the elasticity of demand and the elasticity of revenue. The relationship is quite simple. The change in revenue with respect to price is equal to 1 minus the elasticity of demand. We'll see how that's derived in a moment. This is an important relationship for any business. If they know that their product is elastic or inelastic, they can predict the change in revenue as a result of a change in price. Remember, for the elasticity of demand, values go from minus infinity to 0. Recall also elasticity changes from elastic to inelastic at minus 1. The change in revenue due to the change in price is the marginal revenue. If the good is inelastic, that is, takes a value between minus 1 and 0, then the percentage change in revenue due to a 1% change in price will be positive. We subtract a number between minus 1 and 0 from 1. Thus, the maximum value for the elasticity of revenue is plus 1. Why is that so? In the case of petrol, if the price of petrol goes up, in the short run, the revenue for the petrol companies will increase, because petrol is an inelastic good. On the other hand, in the case of elastic goods, where the elasticity is between minus infinity and minus 1, if we subtract a number greater than minus 1 from 1, we'll have a negative number. So we'll see there that the elasticity for revenue with respect to price is negative. The marginal revenue will decrease if there's an increase in price. For example, if the local takeaway restaurant puts up its price, then people in the neighbourhood might go to a competitor. So overall, the revenue for that restaurant goes down. Now let's look at how we derive this relationship. Revenue as a function of price is equal to price times the quantity demanded. Applying our formula for elasticity to revenue, we'll have the elasticity for revenue is equal to the price on revenue as a function of price times drp dp, the first derivative. We can substitute in price times quantity demanded for R. That gives us P on P times quantity demanded dp of P times dp. Prices cancel out there. That's equal to 1 on quantity demanded times, well, we have a product, so we apply the product rule here. It'll be 1 times quantity demanded plus P times d prime P. We can expand that, so we'll have dp on dp plus P on dp times d prime P. First term there is just 1. The second term is the elasticity of demand. So we've derived the formula for the relationship between the elasticity of revenue and the elasticity of demand.